All right, so it's Lewis structures, and we're looking at basically things like this. So I'm not going to give you the full review unless you just really need it later. But a couple things to remember. Every atom is trying to get its complete octet. For nitrogen, it's trying to get 8 electrons, which means 1, 2, 3, 4, 5, 6, 7, 8. That's what it wants. It wants 8 valence electrons. Hydrogens, they only need 2, and this line represents 2 electrons, so all of the hydrogens are fine. Hydrogens have to be on the end, so they have to be on the outside. They can't have 2 bonds. Okay? So here's this method that I learned, and let's look at CO2. They call this method, I guess pronounced NASL, maybe. It's what you need, what you actually have, how many are shared, and how many are lone pairs. So when we look at the number of electrons we need, each atom wants 8, okay? So this carbon needs 8, plus there are 2 oxygens, and each one of those need 8. This is what we need. And so that's 24. Overall, we need to have 24, whether they are just belonging to one atom or whether they're shared. Then we look at how many we actually have. And this is where the valence electrons come in. And it's been a while since we've talked about that. Carbon, it's in group 14. If you subtract 10, it tells you it has 4 valence electrons. Everything in group 14 has 4 valence electrons. So carbon needs 8, it actually has 4. Plus, then we look at oxygen. It's in group 16. Subtract 10, it has 6 valence electrons. And there are 2 oxygens. So here's how many we actually have. This is 12 plus 4 is 16. So we know how many we have to have. We know how many we actually have. Now we have to figure out how many are going to be shared. So what we're going to do, 24, that's this number right here. Make it a different color. Put that number here. And we're going to subtract out 16. That was this one right here. Okay, so just subtract how many we need and how many we actually have. And that tells us we have to share 8 electrons. Okay. Then there's lone pairs. And for this one, what we have to do, 16, that's this one, minus 8, run out of colors here, and that's how many we're sharing. So we're going to share 8 electrons. We're going to have 8 electrons that are by themselves. Okay. When you start actually drawing the picture, everything is in pairs. This is a shared pair. So I'm going to divide by 2. That tells me I'm going to have 4 lines. Okay, 4 lines. And the lone pairs, they're always 2 paired up together. So you could leave it as 8, but if you always draw them in pairs, It's going to be 4 pairs. 4 pairs of electrons and 4 lines. Now to figure out what it looks like, generally speaking, the first element is going to be in the middle. Okay? So something like this. And I need to make 4 lines here. It's going to be 1, 2, and then I guess we can double up 3 and 4. Okay? So we did this one, check. Then we have 4 lone pairs. And we have to figure out where these go. Look at carbon. Each line is 2 electrons. 2, 4, 6, 8. Carbon's already filled up. But if you look at the oxygens, this one only has 2, 4. There's 6, there's 8, there's 6, there's 8. That's the 4 pairs that we predicted. And this is actually what CO2 looks like as far as Lewis structures go. So I know it's first day back. I know this is a topic you haven't seen in 1 or 2 years. Hopefully it's going to make sense. I'm going to do a few more. And later you can always watch the video again, or we can talk about it again if you need. I mean, if worst case scenario, I can give you the Unit 1 notes filled out and you can look at them again. So maybe. So I'm going to erase some of this and look at another one. Small change, 1 less oxygen. Now it's carbon monoxide. All of the math here is the same, just the numbers are going to change a little bit. So how many electrons do we need? Carbon needs 8. Oxygen needs 8. We need 16 electrons. How many do we actually have? Carbon, number 14 minus 10. Oxygen, group 16, subtract 10. So we have 10 to work with. How many need to be shared? That's this number minus this number. 6. And how many lone pairs or how many lone electrons do we have? That's 10 minus 6. And that's 4. We're going to have 3 lines. We're going to have 2 pairs. There's only one way you can put these 2 things together. Here they are. We need 3 lines. And we need 2 pairs. So let's look at carbon first. 2, 4, 6, 8. And then oxygen, 2, 4, 6, 8. We did this, and we did this, and this is what it should look like. So some things that'll help you at home tomorrow when you're looking at questions 1, 2, and 3 is what you're going to do. They're all about entropy, and they want to know what's got more entropy, or how do you increase the entropy? These are the ways to increase the entropy, and they're in your notes at the top of page 1 on 4.2. Increase the temperature, increase the volume if it's a gas, increase the number of moles of substances, changing states and changing a substance to a mixture, like dissolving it in water. These are all ways to increase the entropy, ways to have more ways to arrange it. Basically, there's more ways you could arrange KBr when dissolved in water than when it's, say, a solid piece of ion. And so these will help you as you look at those ones, numbers 1, 2, and 3. Number 3 actually uses the AP formula, and it is this one. This comes from your AP formula sheet, and you'll run it just like this calculation. So that's something that you'll be working on tomorrow, and the form is already up and present if you need it. So I guess if you went home and did it today, that'd be fine. Wouldn't matter. And what we're going to work on here in class and for the next 10 minutes after I stop the tape has to do with this equation up here. This is the Gibbs free energy equation. This is also on your AP formula sheet. So I'm going to do, let's see what number this is. If you want to open up your problems, I'm going to do 4B. Let me erase all of this. So given the example of 4B, you should be able to do the rest of number 4 and number 5. So they give us a chemical reaction. The reaction itself really doesn't matter. Had they not given us the reaction, we could still do this given the information we have. It's just kind of there. So it gives us some other stuff. We know that delta H equals negative 176. And that's kilojoules per mole. We know that the delta S is negative 284 joules per mole per Kelvin. So this is the information we get for the actual reaction. And we're going to be using this formula because it relates free energy with delta H, which is the enthalpy, the heat, and the delta S, which is the entropy, kind of the amount of disorganization. So both of these two things have a negative sign. The delta H is negative and the delta S is negative. From yesterday's video, take a look at this. When delta H is negative, when delta H is negative and delta S is negative, it works, but it only works at certain temperatures. They have to be low temperatures. And low is a relative term. So the question asks, for each of the following reactions, determine for what temperatures it is spontaneous. You heard what I said about spontaneous yesterday, right? Never write the word spontaneous. Thermodynamically favorable. If you write spontaneous on the AP exam, they will say -1. They don't like that word, even though it's still in modern textbooks. So we know that our question is going to work. The question is just at what temperatures will it work? So for something to be thermodynamically favorable, is delta G positive or negative? Do you remember this from yesterday? So before you say anything, let me find the spot for you here. So look at the second page, and there's a graph or a table, and just to the left of it, there's a bold print sentence. A reaction is thermodynamically favorable when delta G is less than 0. That means negative, right? So we want delta G to be less than 0. And we want to know at what temperatures. And so this is one of those things that comes up in math sometimes where you could actually restate this. We know delta G needs to be less than 0, but that's all we know. Yeah. Make sure I write this down right. Okay, so basically we want this to be negative. So 0 is greater than, because I flipped it, right? That's basically what it's saying. If you've turned this around, that's. And then it's your delta H minus T delta S. So we're going to plug in our numbers, and it's going to tell us at what temperature and below does this work. So my numbers here. There's my delta H minus, we're actually looking for temperature. That's what we want. And our delta S is negative 284. So here's my basic numbers. Now there was one other thing that we wanted to do. Look at the units. This is kilojoules. I talked about this yesterday. And this one's in joules. All of this needs to be in terms of kilojoules. So we're going to convert this one like this. This equation might have made more sense if I wrote it like this. And then we just solve it like any other equation. We're solving it for T. So I have to be positive. So I'm going to